Alright, in this problem we're asked to compute the volume of the solid beneath f of xy equals the square root of 1 minus x squared, and above the region x from negative 1 to 1 cross y 0 to 4, so basically that rectangle. So if you go to GeoGebra and put this in, you get something that kind of looks like this, and it's basically half a cylinder, right? 1 minus x squared is a circle with radius 1. This is solved for z. So it's like z equals 1 minus x squared. So if you squared both sides, you'd get z squared equals 1 minus x squared. And then if you added the x squared over, you'd get z squared plus x squared equals 1. So it's a unit circle in the zx plane, and y can be anything. So this is like the y value. Whoa, sorry. This is like the y value coming out at you this way. This is the y value. Okay? So here's my y value. Here's my x. Maybe I should draw that in there in z. Now, depending on where you're at with visualizing these shapes, if I didn't give you this figure, you know, some of you might be at different points in your understanding. And if you can visualize what this shape is, it might give you some other ideas about how to find the volume other than using calculus. But if we didn't have the shape and we didn't know exactly what it was, then we might rely on calculus. So I just want to talk about this a couple different ways to do this. All right, so this is y equals 4 and x equals 0 here, and this is z equals 1. This is the z-axis coming up here. Sorry, that was sloppy. And that's 1. And then this is your x-axis over here, so this would be like x equals negative 1 and x equals 1 over here. Okay. So, I mean, I almost hate to, it's like, this would be one of those things where I would say, hey, who has an idea? I'm just going to say there's multiple ways to find the volume of this. So maybe pause the video and think about multiple ways to do it, and then we'll talk about a couple of them. Well, one thing that you might be thinking is this is just a cylinder. This is just half a cylinder, right? So, I mean, once I get the shape in my mind, I could just say, well, the volume of a cylinder is pi r squared h, and the radius of this cylinder is 1, and the height of this cylinder is 4. It's like laying on its side. But I only have half a cylinder because it's split in half, so I'd multiply it by a half, my volume, and so I would get 2 pi, and I would go on to the next question. I don't need any calculus. Awesome. Let's practice our calculus a little bit, though. So option 2 would be that we could start slicing this guy up, and so our region, let's see if I can draw it here. We usually draw our region, you know, flat in a two-dimensional way, but let's say we're going to slice it this way. So our slices are going to look like these semicircles here. So here we are fixing a y value, right? I'm picking one particular y value between 0 and 4. So I'll fix that. And then we'll figure out what our x would have to be here. So our x's are going to go from here to here. We have a rectangular region, so the bounds are going to be pretty easy, right? The bounds are just going to go negative 1 to 1, and the y's are going to go 0 to 4, and then we can just put our equation in here. All right, so now looking at integrating this, I'm not too excited about it because I have integrating this with respect to x. That's not a lot of fun. I could think about slicing it the other direction, which does turn out to be pretty easy. You just are going to switch nicely. We don't really have to worry about the bounds when we switch these when they're constants. Basically, when we have a rectangular region, we could just switch these and, oh, let me write it this way. Let's say we could put the x bounds, if we cut it the other direction that way, and then the y bounds like that. Lovely. All right, now this is going to be a lot easier to integrate because this is just a constant now. Okay, awesome. So we could do that. I'm not going to go through those, but you might like to do that and see it comes out to be 2 pi. I want to throw one more option out there. I guess we could consider this under option 2. If I set up this integral, I want to remind you of that bonus property that we had, that if we had some double integral over a region where we could write our f of xy. This is our f of xy. Y could be anything, but it's still f of xy. If we could rewrite that as some function of x and some function of y, then we could split that up into two different integrals, right? We could split it up into the integral bounds for x and multiply that and split it up with the integral bounds for y and put our function of y over here. So could you visualize doing that for this? Can I rewrite this as some function of x and some function of y? It's a little bit tricky. You're going to be like, oh, that was tricky if you don't see it. But if I think of this as a function of x and y, I could say that I could rewrite this as g of x times h of y, where g of x is the square root of 1 minus x squared, and h of y is 1. Yeah, a little tricky. Okay, so I could rewrite then this integral as the integral from negative 1 to 1, 1 minus x squared dx, times the integral from 0 to 4 of just 1 dy. That's kind of handy. Let's just do this one and show it comes out to be 2 pi. Well, so we're into another issue again with this guy because we still can't integrate it like we couldn't before. So how could we do this? Well, we're only in one variable, so we could think of it geometrically. We could think of both of these geometrically. That's kind of fun. That's a good exercise to think about both of these geometrically. These are both in one variable, so we could draw, you know, just regular, whatever, two-dimensional graphs for these guys. So this one is y equals the square root of 1 minus x squared. What does that look like? What's that graph look like? Got it? Good. It's a half a circle, positive, and it's going from negative 1 to 1. So we're going to get this half a circle like that. Okay, and what is this integral telling me I want to do? I want to find the area between the x-axis and this curve. Well, it's just half a circle now, right? So the area of this circle would be pi r squared, which is just pi times 1 squared. We're going to do half of that, so pi times 1 squared. So this integral comes out to be pi over 2. Thinking of it geometrically. All right, how about this integral geometrically? What does this mean? So our function over here is y equals 1. So we would just draw the graph of y equals 1 from 0 to 4. And so this integral is telling me that I want to find this area. All right, what is that area? Well, that area is the area of a rectangle. 1 times 4 is 4. So just thinking of these geometrically, the first integral has area of pi over 2. The second integral has area of 4. And so I come up with 2 pi. All right, just a little bit of mental gymnastics there, thinking about the difference between finding areas in 2D, finding volumes in 3D. We got the same answer. That was kind of neat.